Welcome back. This is part 2 of the last lesson in our chapter 1 of Unit D. So we're moving on with nuclear reactions. We're going to look at 2 different types of nuclear reactions. There's fusion and then there's fission. And you would have seen fusion before. Nuclear fusion is when 2 smaller nuclei join together to form a large nucleus, a larger element. And when they do that, they release energy, a lot of energy. Do you remember where this happens? This might look very familiar to you. You have hydrogen coming together to form helium. This is happening in our sun. Okay, so fusion is what's happening in the sun, the type of nuclear reaction. Okay. So we cannot yet harness nuclear fusion to create energy yet, not yet, but it's definitely something that is being worked on. We can't contain the energy yet, but it's definitely something that's being worked on. That's one of the goals. The one nice thing about that, if you could do that reaction, the only byproducts are neutrons and heliums, which are pretty neutral substances, so you don't get that radioactive decay, the same problem with that. So anyway, that's something that's being worked on. All right, fission, that is typically what you're seeing when we're talking about nuclear reactors. This is what's happening. You have a large nucleus, like uranium, being hit with a neutron, and then that large nucleus is getting broken down into smaller nuclei, so smaller elements. Yeah, and then these nuclei, these are unstable, and they can again hit more nuclei, and it's kind of like a reaction that keeps going, like a chain reaction. It's very difficult to control this reaction because they're so unstable. Okay. So they just keep going. These neutrons are created, and it just hits more uranium and making more unstable compounds, et cetera, et cetera. So when you break that uranium nucleus, you're getting smaller nucleus, but you're also getting neutrons, and you can see you get 3 times the number of neutrons that you started with. So it's kind of like the reaction just gets going really fast. So it's very difficult to control. So that's the reaction that is happening in that or similar reaction is happening in a lot of the nuclear reactors. One nuclear reactor you should know the name of is the CANDU reactor. It is actually called the Canadian Deuterium Uranium Reactor. All right. And yeah, it's a nuclear fission reaction that's producing the reaction. But how do you actually turn nuclear energy into electricity? Well, this is going to look very similar to the coal electrical energy generation. You'll see there's a lot of similarities. Basically, by the time you get to this point, it's similar. Okay, so you see the steam turning the turbine, right? Steam turning the turbine, which turns the generator, which produces the electricity. So that part here is the same as with coal. Okay, the difference is that you are starting with this internuclear potential energy, this potential energy that's in the nucleus. And that is a big difference. You've got a reaction happening inside of a containment structure. Basically, your nuclear reaction is happening, and it heats water. Right? You create steam, and that steam goes and turns the turbine. So instead of burning the coal, you've got a nuclear reaction that is causing that heat. Okay. We'll get more in detail into that in a bit here. So there's different components of the reactors that you should understand. There's fuel. In this case is uranium-235. And you can see a picture of it here. We have a moderator. You should understand what a moderator is. It's used to slow down the reaction, to kind of keep some of those neutrons, too many neutrons that have been released, to slow them down. So they use something called heavy water, which is water basically, but instead of hydrogen, it's it's like a different isotope of water, or a different isotope of hydrogen. Just need to know that it's used to slow down the reaction. So uranium is what's used in that CANDU reactor, and you can see all around the world where the uranium is found. You can see Australia has quite a lot of uranium, but so does Canada, 12% of the world's uranium. This is pretty impressive, interesting. Okay, some other parts and components to the CANDU reactor are the control rods. These also help to control the rate of fission so it doesn't get out of control. They absorb neutrons in an emergency and help shut it down. You have special shielding around these nuclear reactors. So you can see here, you have them usually made of steel or concrete so that any radiation that does get released in the reaction doesn't leave the reactor. There's just a bit of a comparison here between a coal-fired power plant and a nuclear power plant. The original energy source for both of them are non-renewable energy sources. Uranium-235 is not something that's renewable, like coal. What's the form of the original energy source? For coal, it's the chemical potential energy in coal, and for a nuclear reaction in uranium, it's the internuclear potential that's in there. So we're talking at the nuclear level instead of the chemical potential level. And what reaction is used to release the energy from this source? It's combustion for coal, and it's nuclear fission. By bombarding it with neutrons. It's nuclear fission that's happening in uranium. And the energy conversions, make sure you can see the difference between these. So for coal, it starts with the sun because the sun grows the plants that the animals eat before they break down over time pressure, long time pressure, and turn into chemical potential energy that we then burn and turn a turbine to get the kinetic, and that creates the electrical in the generator. Whereas the nuclear power plant, it's the nuclear energy that's inside that uranium, and which you then react in a fission reaction, and you get thermal and kinetic. Thermal energy coming out that you heat the water. Water turns to steam, turns the generator. Generator creates electricity. Okay. So you can see the last three energy changes are the same whether you're talking about coal or you're talking about nuclear. All right, you're going to do a whole assignment on the benefits and costs of nuclear energy. So I'm not going to go over this because you have a whole assignment on it and you can read this. And there's lots of calculations that we need to get to. So I don't want to have a 45-minute lesson. Again, same thing, you can read through that storage. Okay, so this is the formula that I wanted to get to before we run out of too much time here. So you've probably seen this before, E equals mc squared. This is Albert Einstein's famous equation, E equals mc squared, and you're finally going to use this equation. Yes. Okay, so what does it mean? Well, technically it's delta E, which means whenever you see delta, that triangle means change in energy or energy change, and energy is just measured in joules. Then we have delta M. So yeah, it's not just M, it's delta M. So it's the change in the masses. Okay, so it's the amount of mass that was converted to the energy. And then we have C, which you've seen before, the speed of light or speed of electromagnetic radiation. And remember, you got to square it. Okay, so you got to not multiply by 2, square it. So you're multiplying by itself, right? This formula is on page 8 of your data booklet. And this formula is saying that mass can be converted into energy. Okay, so whatever mass is lost, if you multiply it by the square of the speed of light, that tells you how much energy is gained or lost. Okay, and a tiny loss of mass results in a lot of energy. So we can use this formula to figure out the amount of energy that a nuclear reaction will create. All right, so here's an example question. In the fission of 1 mole of beryllium-8, the mass of the products is determined to be 2.29 times 10 to the negative 5 kilograms less than the mass of the reactants. Calculate the change in energy that corresponds to this with this change in mass. Okay, so here we're going to use Einstein's formula. We've got the change of energy is equal to the change in mass, or the mass lost, times the speed of light squared. So our change of energy, they actually give that to us in our questions. We don't have to calculate it this time, but we will in the future. 10 to the 5 kilograms. All right, so that's the mass difference between the products and the reactants. How much mass was lost. And then we're going to multiply that by the speed of light, which you should know by now is 3.0 times 10 to the 8 meters per second. And we're going to square that. So we're going to square this first, right? So this should become 9. And then we're going to multiply by this number. All right, so pause and do that on your calculator. All right, now this should be your answer. So if you've done this and you've squared this number first and multiplied by this number, this should be your answer here. 2.061 times 10 to the 12 joules. That's a lot of energy, right? All righty. Now, because it's a nuclear reaction, lots of energy in these cases. So this next question is going to be a little bit more detailed for sure on what you need to be able to do. So you're still going to be using E equals mc squared though at some point. Calculate the energy released by the alpha decay of radium-226. Now notice they don't tell you anything about the amount of mass that was lost or anything like that. So to figure out the mass loss, we need to know what the reaction looks like. So let's write out the alpha decay for radium-226. So pause this and see if you can write out the formula for the reaction of radium-226. Okay, so radium, if you look in your data table, in your periodic table, radium has an atomic number of 88, and they tell us the mass number is 226. And it's going to alpha decay. Alpha means you're releasing a helium atom. And then what is, oops, that's a 2. There we go. And then what's the other substance going to be? Well, our 4 has to add up to give us 226. So we're going to have 222 here for our mass number. And 2 plus 86 gives us 88. If you're not sure how to balance this, make sure you go back to the last lesson. Number 86 is radon, is the atomic number for radon. So this is our actual nuclear reaction that's happening here. So to actually calculate the energy, we need to find the amount of mass that was lost in this nuclear reaction. In order to do this, we need to find the masses of the reactants and the products. All right, so in this case, we need to now figure out how much mass was lost. So our products are going to have less mass. Our products here are going to have less mass than our reactant. So we need to add up the masses of our products. So radon 222. This is all on page 8 in your data booklet. Okay, these are the masses of these different isotopes. And you can see it has a 222. So this mass is 222.01757. Don't worry about the units or anything like that right now. We're going to add that to the mass of the helium. The helium, here we go. It's 4.00151. All right, and then we have our radium-226. That's this, radium-226. You got to watch those mass numbers. Make sure you got the right one. And it's 226.02540. All right, so we want the mass of our products. And this is our mass of our reactants. And so we're going to take the mass of our products minus the mass of the reactants. So we add our products all together. So we're going to go 4.0 0.00151 plus 222.01757. So our mass of our products here is 226.01908. And then we're going to subtract the mass of our reactant here, which is 226.02540. You can put that all in your calculator and see what you get. And you should get 0.00632. It's a negative number because we've lost that amount of mass. Now, this isn't the exact number because we got to watch for this here, the units. So what are the units? So our actual mass that is lost, or the change in mass, is equal to negative 0.00632. And then we're going to use these units that are here, times 10 to the negative 3 kilograms per mole. So we could have put these units in at the beginning before we did all the adding and stuff, but it's so much easier to throw it in right here at the end. So we've just found our change in mass. Now we can use Einstein's equation to figure out what happened to how much energy did this mass form. We lost this mass. It didn't just go nowhere. It turned into energy. So our change in energy is equal to our change in mass times the speed of light squared. So our change in mass is negative 0.00632 times 10 to the negative 3 kilograms per mole. Actually, the moles go away because we multiplied those out. And then our speed of light is 3.0 times 10 to the 8. If you forget, that's also from our last unit on the electromagnetic spectrum page. What page was that? 4 or something like that? Okay, so square this number, multiply it by this mass, and see what you get. So when you square that speed of light, you should get that number. Then you're going to just multiply it by our negative 0.00632 times 10 to the negative 3. Okay, and so when we multiply these together, we should get negative 5.688 times 10 to the 11. All right. And from back in unit C or B or whatever unit that was, we know that energy is measured in joules. So that's in joules. So you have the answer keys right here. Make sure you go through this, do this on your calculator so you understand how to do that calculation. Definitely a little tricky if you haven't practiced it. All right, I'm going to do one more example, even though there's a few more in the lesson, but we'll do one more, and then you can use the answer keys that are provided to check your answers on the last two. Calculate the energy released by the alpha decay of polonium-210. So because they don't give us anything about the mass, we can't just hop to Einstein's formula because we don't know what the change in mass is. So we have to figure out what the change in mass is for this nuclear reaction here. So let's write out polonium. So polonium is, let's look that up on our periodic table. You can also find it on page 8. If you look up polonium-210, it'll actually give you the isotope notation for polonium. So polonium is PO, and it's 210, and the atomic number is 84. And it's going through alpha decay, which again is a helium atom. Oh, why do I keep putting a 0 there? I did that last time too. And it's a 2. Okay, and then let's see what the leftover is. So we're going to have a atomic number of 82. 82 plus 2 gives us 84. And then 206 plus 4 gives us 210. So our equation is balanced here. If we look up 82 on our periodic table, we will see that gives us the element of lead, Pb. So polonium is decaying into lead. Now let's see how much energy or mass is lost in this process. So we're going to find the mass of the products, and then we'll subtract the mass of the reactants. So the mass of products and the mass of reactants. Let's look them up. So these are all looked up in our chart on page 8 again. So look them all up and see if you get them right. Okay, so we've got lead 206 with its mass from the chart, helium or alpha particle with its mass, and the polonium 210 with its mass. We're going to add up our products first and then subtract our reactants to find the difference. Okay, so our two products add up to 209.97601, and then I'm going to subtract that from the polonium. And that gives us a mass change of 0.00685, and that's negative again. We're losing mass. And remember, we go back and we just check our units, and our units are all going to be times 10 to the negative 3 kilograms. All right, so our change in mass, but we want to know how much energy is released. So this amount of mass is lost. So what does that turn into in energy? We're going to use Einstein's formula. Equals change of mass times the speed of light squared. So our change of mass is negative 0.00685 times 10 to the negative 3 kilograms. Our speed of light is still 3.0 times 10 to the 8 meters per second squared. So square this and then multiply by this number and see if you get the right answer. All right, and our answer is negative 6.85 times 10 to the negative 6 joules. So that's how much energy is produced when that mass is lost in this nuclear reaction. So if we can harness that energy, that's a lot of energy for just 1 mole. That's a lot of energy that we can keep and use again. All right, so there are a couple more questions that you can try out, and the answers are there. If you're having any problems, let me know and we can go over this together.